Well, hi there. So today we're just going to do a quick little introduction into our next unit, which is about something called a confidence interval. And for the next little bit, for the next couple of units, we're going to focus specifically on proportions. So let's go ahead and get started. So first, let's look at this vocabulary term called a point estimate. So a point estimate basically uses a single statistic based on sample data to estimate a population parameter. So if I want to know something about my population, one way to do that is to take a sample, hopefully a random sample, and then calculate the statistic, the proportion from that sample or the mean from that sample, and use that as an estimate for the population. So for example, it says Gallup reported that 32% of parents have participated in surveys in their child's school. So they're trying to estimate the true proportion of all parents who participate in surveys. So they took a sample. They took a sample, and in that sample, 32% participated in surveys. So we're using that as an estimate. So it's a point estimate of the true proportion of parents in the US who participate in school surveys. So it's just one number that is estimating the population. So just to look at a couple of examples, I'm going to give you two scenarios, and we're going to think about which or what is the point estimate we would use to estimate our parameter. So on A, what proportion P of US adults would classify themselves as vegan or vegetarian? A Pew Research study report surveyed 1,473 randomly selected US adults. Of those, 124 said that they were vegan or vegetarian. All right, so in that situation, our parameter, the thing that we're trying to find out is the proportion of all US adults who say that they're vegan or vegetarian. But obviously, it's really hard for us to do that to actually find out from all Americans. So we're going to take a sample. So our point estimate would be, oops, the proportion of the sample who say that they're vegan or vegetarian. And we're going to calculate that by just doing the number who said they were vegan or vegetarian divided by the total. So 124 divided by 1473, which is 0.084. So that 0.084 is our point estimate for that proportion we're looking for. Okay, part B, quality control inspectors want to estimate the mean lifetime mu of the AA batteries produced each hour at a factory. They select a random sample of 50 batteries during each hour of production. For one sample, the average lifetime was 16.7 hours with a standard deviation of 0.664 hours. So again, our parameter is the true mean lifetime for all AA batteries produced each hour, but they produce so many batteries that it would be a ridiculous amount of work to actually calculate the true mean for all the batteries. So they're going to take a sample, and their point estimate would be the mean battery lifetime of the sample of 50 batteries that they took, which was 16.7. So that is our point estimate for that situation. So again, a point estimate uses a single statistic based on sample data to estimate a population parameter. So here's the problem with that. It is a simple approach, pretty quick and simple. Take a sample, find the proportion or mean from that sample. Done. There's my estimate. I can move on with my life. But it is not always very precise because we know there's always going to be some amount of variation. Even when we take random samples, we know that there's variation. That random sample is not going to be perfect. There are ways to make it a little bit more precise, but it's not always going to be perfect. So think about that 32% came from a sample. If I take another sample of parents and ask them, how many of you have completed surveys for your child's school, are we always going to get the exact same statistic? Probably not. So that's where confidence intervals come in. So confidence interval is also used to estimate the unknown population parameter, but we're going to do it with an interval, meaning we have something called a margin of error. So our basic formula, and we're going to come back to this in class and do a little bit more specifically, but our basic formula for confidence interval is we have a statistic, which comes from the sample, same as what we did for point estimate. It's just that number from the sample, plus minus a margin of error. So Gallup poll reported that 32% of parents have participated in surveys in their child's school, and the margin of error is 3%. So 32% is the statistic. Margin of error is plus minus 3%. So our total interval would be 32 minus 3, which is 29. and then 32 plus 3, which is 35. So our interval is from 29% to 35%. So where does that margin of error come from, that 3%? So I'm going to go through this fairly quickly right now and know that we are going to break this down much more slowly during class when we go over this in class. But to give you a little bit more background information, that Gallup sample for 32% consisted of 967 parents, in which 309 of them said that they participate in surveys in their child's school. So 309 out of 967 comes out to about 0.32. So that's where that proportion came from, that point estimate. So here's where the interval part comes from. As long as we know our population is normally distributed, then we can say that about 95% of samples should be within about 2 standard deviations of the mean. Now, where that came from is, if you remember forever ago, when we first started talking about normal model, we had this thing called the empirical rule, which said that if a distribution is roughly normal, if a population is roughly normal, then about 68% of the values in that distribution should be within 1 standard deviation of the mean, 95% should be within 2 standard deviations of the mean, and it was 99.7% within 3 standard deviations. So as long as our population is normally distributed, then we can say that about 95% of samples should give us a sample proportion, an estimate that is within about 2 standard deviations of the mean. And that just came straight from that empirical rule. But what's the standard deviation? Well, technically, the standard deviation would be p, or square root of p times 1 minus p over n, which we've learned when we talked about sampling distributions. So part of the problem is I don't actually know what p is. I only know p hat because I don't know what's true about the population. But I can use that p hat as an estimate to find a standard deviation. So square root of 0.32 times 1 minus 0.32 divided by n gives me about 0.015. So then 2 standard deviations to get me to that 95% is about 0.03. So that's where it came from. I know that, again, we will break this down much more slowly into steps later in class, but that's kind of where it comes from. It comes from this like percentage value of how far away do I want to be from the true mean, and then it comes from that sample proportion data. How we interpret a confidence interval. So for the Gallup poll example, the point estimate was 32% and the margin of error was 3%. So what we might say is, so again, 29 to 35. So what we might say is that we are 95% confident. Why 95%? Because we went about 2 standard deviations either way. And that's where the 95% came from, is that 2 standard deviations. So we're about 95% confident that between 29 and 35% of all parents have participated in surveys. So we're giving it a range, and then we're giving it what we call a confidence level that's based on how many standard deviations away did I go. Okay. What affects margin of error? So obviously, we can maybe think of some things, how far out we go, how many standard deviations away we go affects margin of error, because that's relating to that confidence level. But sample size also affects margin of error, and then what p hat is, what our sample proportion is, also affects margin of error. But I want to look at that just a little bit more as a visual. So let's say we have a situation where the true population proportion is 0.5. Now again, in real life, we're not going to know what the true population proportion is. We're using a sample to estimate it. But let's say in real life that this example, that the true population proportion is 0.5. And let's keep our confidence level at a 95%. Again, that just means we're going out 2 standard deviations either way to get our margin of error. And let's keep our sample size at 20. So when I take a sample, right, this one is showing that we got a sample proportion of 0.55, so a little bit higher than the true proportion, but we expect some variability. So that margin of error is saying plus or minus 0.22. So the margin of error is pretty wide. So we're going 55% plus or minus 22%. So that's a pretty wide interval. But that interval does happen to capture that true population proportion of 0.5. But what happens if I take another sample? If I take another sample, I get a slightly different sample proportion, and plus and minus my margin of error, I'm still capturing the true population parameter. If I do another sample, for this sample, I got a really, really high sample proportion. So even that margin of error is not quite capturing the 0.5 that was the true proportion. And if I keep doing this, if I keep taking a bunch of samples, what we'll notice is that most of the time, my interval is capturing that 0.5 true proportion, right? So only one time did we not capture it, which is, again, why an interval is really useful. So let's see what happens if I change things. So in the example we did with the Gallup survey, or the example that they did, our sample size was really big. It was almost 1,000. So I'm going to pull the sample size up to 1,000, and we're going to see what happens to that interval. So if I take a sample this time, well, now my sample proportion is 0.506, but look at my interval. Look at how small it is, right? So if I do that, my interval, upping my sample size makes my interval much, much smaller. But notice that I'm still capturing that true proportion most of the time. So far I've had 2 intervals that didn't get there, but most of the time I'm still capturing that true population. So upping the sample size made the interval way smaller, but I'm still capturing that true proportion most of the time. Okay, let's see what happens if I keep my sample size at 1,000, but if I up my confidence level. So if I went up to, instead of 95, I'm going to do 99. Okay, so when I do that, my interval, notice it might be kind of hard to tell, but my interval does get a bit wider. And when I do this, on that example, I'm capturing the true proportion more of the time. I'm going to go back to 95 and make my sample size a little smaller. Let's actually go down to 90% confident, right? So we can kind of see that those are things that affect. If I change the proportion, that's going to have a little bit of an effect on the interval as well. Notice that with a lower confidence level, right, I'm capturing the true proportion a little bit less often. So there's a lot of things, and like I said, we'll go through this a little bit more, but it's good to notice the things that do affect the margin of error that have an impact on it. The last thing I'm going to show you, and it's something that we'll talk about more in class, had to do with something we noticed here when I changed that confidence level. So interpreting a confidence level. So for the Gallup poll example, the confidence level used was 95%. And I mentioned that that had to do with I'm going out about 2 standard deviations either way from my point estimate. That's the amount I'm going, and it's 95% confidence. So the way we interpret a confidence level is to say, if I take many, many samples of 967 parents, if I do that whole process many, many times over and over and over and over and over and over again, about 95% of those intervals that I calculate from all those different samples that I take, about 95% of those intervals should include the true percentage of parents who answer school surveys. So again, if I go back to that visual, right, when I take samples, in this case, I have the true proportion set at 0.74. Okay. Most of the time, my interval is capturing that true proportion. 1 out of a total of 25 intervals missed it. So my confidence level is saying if I repeat this process many, many times, right, about that percent or 95% of the intervals we calculate should include that true proportion of parents that we're trying to estimate. Okay, we'll talk about this more in class. Obviously, this is just a first little introduction to an interval. So we're going to stop there for now, and we'll talk more in class.